Hello and welcome to ResearchPod. Thank you for listening and joining us today. In this episode, we'll delve into the research of Dr. Johannes Schaffert of the Gas- und Wärme Institut, or Gas and Heating Institute in English, in the city of Essen, Germany. Johannes Schaffert and his colleagues have been investigating how the German energy system can become more green by reducing greenhouse gas emissions. Decarbonising energy production requires power plant operators to change to green technology. This, therefore, has to be profitable. Using models of the German energy system and realistic future scenarios, Dr. Schaffert and his research partners have been investigating the regulatory system that will be needed to enable reductions in greenhouse gas emissions. In particular, the authors have been conducting a business analysis for turning renewable energy, such as electricity, into synthetic hydrogen gas and green methane. As of the time of this podcast release, the German federal government has committed to reaching a 100% reduction in greenhouse gas emissions by 2045. To turn this into a reality, there are roadmaps for the future transformation of the German energy system. These have local, regional and national targets, as well as models of the energy potentials. These assess the power plant, storage and grid capacities required for achieving these targets in renewable energy and energy storage. Models of the energy system and the energy market help to evaluate future scenarios and shape better decision-making. There are a number of these computerized systems in existence. When different models are combined together, this can enhance results, but coupling models is a challenge. Macroeconomic planning, for instance, needs to take into account the decision-making of individual stakeholders. This can be done by using different models and passing feedback between them to see how different assumptions result in different scenarios. By coupling complementary energy system models, the adjustments in the regulatory and financial framework to become carbon neutral become clear. Dr. Schaffert at the Gas and Heating Institute, GWI, and his colleagues have been using this technique to examine how realistic it is for German energy companies to construct plants that turn renewable electricity into synthetic hydrogen gas and methane. These power-to-gas plants are a key way to compensate for the variability of renewable energy and to reduce reliance on high-carbon fuels. Power-to-gas is likely to be technically viable to create the infrastructure underpinning greener gas goals, potentially as early as 2030. But what subsidies will be necessary to incentivise operators to invest in the technology? Looking at a business analysis of the profitability of power-to-gas is important to determine whether energy suppliers will invest in the technology. Turning power into gas can be done in different ways. Two key technologies were chosen for inclusion in the analysis. These are proton exchange membrane electrolysis and technical methanation. The models also include realistic near-future possibilities for technical developments such as the commercial use of biomethane using manure and sewage sludge alongside synthetic hydrogen. Combining the data on existing plant and infrastructure inventory within Germany with provision for the possible technology developmental paths requires some assumptions. Medium scenarios were chosen and generic assumptions made around socio-economic issues such as fuel demands, using normative projections that seem plausible from the perspective of 2020, when the modelling was done. The assumptions have been published online. In order to analyse the German energy system accurately, Dr. Schaffert and colleagues had to consider the balancing effects of the European power grid. So the model had to include the countries that neighbour Germany, as well as Italy, Sweden and Norway. The models assumed that hydrogen is produced domestically within Germany and that natural gas can be imported without limit at national borders. However, the model did not include energy import options for liquefied natural gas, biogas or hydrogen. Even as recently as this podcast's writing, in a swift reaction to the 2022 energy crisis, Germany has built facilities for importing LNG, including import options for liquefied biomethane or hydrogen. These new options will be part of future research done in the project Roadmap Gas Transition, which the same partner institutes carry out. As this example shows, the social, political and economic context for the future is always difficult to predict, and since the modelling was done in 2020, there have been changes to the German energy sector, which will be reflected in the scenarios of the follow-up project. The analysis included almost 100 different technologies, in different sectors such as electricity, heating and transport. Capacity expansion was a key issue, as well as the service life of power plants and the potential for replacing them with newer technology when they reach their end of life. Although realistic choices were made about the potential for technological improvement, it is possible that technology could advance at a far greater pace or far slower than assumed in these evaluations. Natural gas and hydrogen technology is a key enabler for decarbonisation. Dr. Schaffert had to look at the gas pipelines, including both their existing capabilities and the planned expansion, to see what their transport capacities were. The potential for these pipelines to transport gas around Germany and the rate at which it is transported was worked out using publicly available data, and the potential for building extra pipelines within Germany was modelled from 2030. Another important factor was gas storage. Hydrogen gas can be safely stored underground. There are different ways of doing this. One possibility is to convert old salt caverns, as is currently demonstrated at the Etzel cavern field. There are many of these in northern Germany and significant potential to build many more of them. The potential for expanding the use of salt caverns for storing the hydrogen was included in the models. Another option is to use depleted oil and gas fields, or aquifers, or other porous rocks. However, the research on the feasibility and safety of these is still ongoing, so it had to be excluded from the analysis. The case study breakthrough was partly through coupling two different computer models, which provide different perspectives on the German energy system. Remix and Mugriflex are two different models which examine different facets of the system. By applying these in a harmonised, partially coupled manner, the future energy system can be assessed and evaluate if the regulatory framework is suitable to implement the desired overall system development. An integrated analysis of the business perspective within the given regulatory framework and alternative frameworks can be explored. The realistic outlook for different levels of subsidies can therefore be assessed and addressed. Remix is a model that analyses infrastructures in future integrated energy systems in spatial and temporal resolution. Although the original use was in power, it now encompasses electric mobility, heating and hydrogen. Mugriflex is a model that analyses the operation and profitability of individual energy systems from a business perspective. The results can be compared with what is desirable from the macroeconomic view to achieve the climate targets. Dr. Schaffert and colleagues partially coupled these two models by feeding the outputs of Remix into Mugriflex. This integrated analysis therefore considers how the overall energy system would develop and operate with different levels of government funding to incentivise green energy. The analysis indicate that today's regulatory framework is inadequate for realising the investments that are optimal from an economic perspective and needed to meet the climate goals. Consequently, the development of power-to-gas plants requires additional incentives. To enable the emerging demand for hydrogen to be met, commissioning the first hydrogen pipelines by 2030 is necessary. The German regulatory regime of 2020 will not sufficiently support energy transition, with the likelihood that investment decisions will come too late to achieve the government's green targets. According to the political target, coal power plants are phased out potentially almost entirely by 2030. On- and offshore wind turbines and solar panels will become more prevalent over coming years as well. Hydrogen infrastructure is likely to play a central role in the development of green technology. The models indicate a continuous growth using first natural gas, then biomethane and synthetic methane. However, converting power to gas is not likely to be cost-effective from a business perspective until the scenario year 2050, unless there is a change in the regulatory framework. The continuing need for governments to provide some form of premium payment to incentivise green technology is not surprising, as other researchers have reached similar conclusions. To create a favourable investment environment will require some sort of incentive. Adjustments to the current regulatory environment are needed to meet the greenhouse gas emissions target the German federal government has committed to. Although green technologies like turning power to gas are viable potentially as early as 2030, the business analysis shows that operators will need an incentive to adopt the practice. The financial gap for plant operators and energy producers needs to be addressed. Otherwise, Germany will struggle to meet their targets for the reduction in greenhouse gas emissions. Although turning power into gas is likely to be feasible in the near future, to expand the hydrogen infrastructure and transform the energy system will need an adjustment of the regulatory framework. That's all for now. Thanks for listening, and be sure to read more from Dr. Schaffert and his colleagues, with their research paper linked to in the show notes for this episode. Until next time, don't forget to subscribe to ResearchPod for more detailed breakdowns of the latest academic research. See you again soon.